So my name is Gabriel. Here are a few facts about me. I'm an OSDB internal principal consultant at Pythian. I'm an automation superfan. I'm currently working on my master thesis, something related to machine learning, group discovery, trying to. I'm a husband and father of a boy and a girl, and I'm based out of Buenos Aires, Argentina, the land of the Pope, Messi, the Queen of the Netherlands, tango, so on. Nope, so that's Brazil. Argentina is actually down there. We used to get that all the time. So the goal of this session is to kind of share with you a project that came to us and the different design decisions we made and the final architecture we came up with. So we're going to talk about the requirements, the different options we evaluated, the final architecture, some failure scenarios, where are the limitations, and then we will have some time for Q&A, hopefully. So let's talk about the requirements first. This customer was already in Azure, so they wanted their architecture to be in Azure, in the cloud. They wanted to have their application on 3 different regions for geolocality, right? They wanted their customers to be able to access their data from a local data center. So all data needs to be available on all the regions. There was, just partitioning the data by region was not possible. And they were using MySQL as a database backend, so they wanted to stick to that. And of course, they wanted this architecture to be as resilient as possible, right? So there are a couple of considerations. This is an interactive application, so there's a CDN approach. So using a content delivery network or something like that, was not an option. And the workload was mostly reads. So of course, it's read-write, but you will get only a small proportion of writes. So this is what we knew about this architecture. So we knew that we were going to have 3 regions. We were going to have 3 applications, or 1 application on each region. They were going to use Azure Traffic Manager to distribute the client requests to the different regions based on proximity. And at the same time, they were going to use this endpoint monitor feature. So in case an application server is down, or it's not responsive, the Azure Traffic Manager will be smart enough to send that to the next nearest region. So we also knew that all regions were going to be connected using VPN gateways. So that would provide also IPsec encryption. And just as a side note, when you're using this type of gateways, communications are not actually going through the open internet, but they are going through the Azure's backbone. So this is what we knew, and so we needed to start, figuring out how to fill the blanks. So we started with data replication, right? We need to understand how we're going to replicate the data across the different regions. So it is an attractive option to think in any WS-rep based solution, virtually synchronous solution, where you can actually write and read on your local database copy, right? And then let WS-rep take care of replication and any conflicts. So the problem with WS-rep is that it's very sensitive to latency, right? Every operation needs to be, every transaction that is executed needs to be certified on the other 2 nodes. So if you're writing a transaction on the West Europe region, that operation needs to be certified on the other 2 across those 1 links. And of course, the slowest 1 link will limit your transaction throughput. And we were not able to find any SLAs in regards to latency or availability for cross-region links. So we thought up, we stayed out of this option. So then we move into a single master solution, and for single master, you have 2 options. You could go with a standard asynchronous replication, or you could think of semi-synchronous. But in this case, semi-synchronous would not do much for us. You still need to cross. You still need to connect from 1 region to the master region. So you have that first hop, and then if you're using semi-synchronous, you will need to wait for 1 or more slaves to read from that binary log and to have that to copy that event locally. So you would not be in a better situation, right? You will have this cross-region hop to get to the master, and then you will have to wait for one of the slaves, or one or more slaves, to read that binary entry. So, and again, it's important to remember that none of these solutions are gonna allow you to get rid of inconsistent reads, right? There is not a synchronous solution for this. And you will still need to, the different solutions will reduce the amount of lag, or the amount of, the odds of getting an inconsistent read, but you will not get rid of that. So we move forward with the synchronous replication. So now, once we have that, we started to figure out how to route the database traffic through to the different nodes, right? So we wanted our applications to read from the local replica. So we wanted reads to go to the local slave, but of course we needed writes to go to the central master, and that's so we needed read-write splitting for sure. We also need something to take care of failures, right? In case that master fails, we need a layer to take care of redirecting the writes to the new master. And if in case the slave fails as well, you will also need something to take care of those reads. So of course we are talking about proxy here, and the other decision that you need to do is where to put that proxy. So are you going to put it on the database server? Are you going to put it as in a middle layer, or at the client level? So we definitely didn't want the proxy on the database server. We wanted those two components to be independent. So we didn't want the proxy to fail if the compute instance running the database fails. At the same time, having the proxy on the client level, it's definitely an option. But you will have to modify your provisioning process to include the proxy, and also have your configuration centralized somewhere, so all your applications are running the same version of your proxy configuration. So in this case, we went with a middle layer. So we found out that having this, even though you will have an additional hop, for your database operation to reach database. On 2 out of 3 regions, your writes still need to cross to the master region, and so that's definitely more important than the additional local hop. And at the same time, if your proxy is using caching, you could reduce the amount of reads that actually needs to go to the slave. So that's how we decided to go with a middle layer, and we proved that it was good enough for our architecture. So the product options here, we started with max scale. That was going to be the product for us. But then a few days after we decided this, max scale 2.0 came out with the BSL license model, and that kind of dissuaded the customer from going with that option, and we start considering ProxySQL, right, which is getting a lot of, this project is from last year, sorry. So even last year, ProxySQL was gaining a lot of traction. There was interesting benchmarks available, and we decided to, us and the customer decided to move forward with that technology, under the risk that the ProxySQL community was going to be small, and we knew that. And the product was, was not that mature. So I'm not going to go into the ProxySQL configuration details. Just wanted to tell you that we configure read-write splitting using different host groups, and we also use waits for the servers to allow read failover. So you will have different read servers on your read host group, and if the first server or the server with the higher weight is not available anymore, then ProxySQL will choose the next slave with a higher weight. Also for after write operations, since ProxySQL has its own regular expression, I mean the rules are based on regular expressions. You can include a specific comment on your SQL for queries that need a strong consistency, and the proxy will be able to route those to the master. And as I said before, also query caching is available. It is a TTL-based cache, so there's no cache invalidation, but it could be good enough for several scenarios. Again, usually applications are working with MySQL and with replication are used to deal with stale data. So if you set a TTL that is not large enough, you could also get some benefit from a TTL-based cache. So we had our replication, we had our proxy layer. Now we needed to find out a topology manager to fix our topology in case the master fails. So and we needed, I mean, not only to this topology manager, we needed not only to fix our topology, but also to take care of fencing, take care of that dead slave, and make sure it won't cause any problems if it comes back to life. So we needed a solution that take care of all that, and by fencing. We knew we needed a double strategy or a mixed strategy. So on one hand, we need to make sure that server that master that was considered as dead was down, and for that we could use the Azure API to try to shut down that server. Of course, we know that those requests are not synchronous, and there's a time for that request to be processed, and also there's some time for that instance to be down. So that's why we have that other part of the strategy where we're going to be removing the servers from the proxy, and to prevent, so the proxy will no longer be aware of that master after a failure. The point is that you need one of those two factors to succeed before allowing failover to proceed, right? Otherwise, the failover may not be safe because you don't know if the master if the master is available again. ProxySQL will start sending writes to it, and of course, if the proxy is still aware of that server, that same risk is still, risk is still an option. So we chose MHA directly. I'm just mentioning GitHub Orchestrator here. I'm pretty sure it could have been an option as well, but we did not evaluate that at that time. So this is how the final architecture would look like. You have your 3 regions. You have a proxy running in each region. You have a single master. In this case, it's West Europe, and so all writes all the red arrows are going directly to that region, and all reads are going to a local copy. So it's important to mention that we did not choose that region. We went with a US region because latency. We found out that latency for that region was much better. So that's an important thing, right? If you need to choose what your default region is going to be, make sure that's the one with the lower latency. So we have our topology manager there, and there's a few slaves that were added there also for backup purposes. So here, just a simple case here, or one scenario is that if for some reason the region fails, Azure does there's no such a thing as availability zones in Azure, or in fact, I think there are. This is in a preview state. So the only thing you have is availability sets that will ensure that your VMs are running on different cabinets or different racks with different power supply and all that, but they are still running on the same data center. So if for some reason that data center goes down, then the topology manager will choose one of the other slaves as the new master, and we'll redirect the writes to that new master, and of course it will reconnect, in this case DB1 as a slave of DB3, and of course now reads and writes for the Southeast Asia region are going to be local. So other failure scenarios. So we talk about region failure. What happened if something fails at the application layer? Well, we did not have a lot of decision on that, but I think autoscaling was being used there. So you can set a minimum amount of servers on your autoscale group, and if for some reason a server fails or an instance is no longer available, then autoscale should take care of creating a new instance. Proxy layer failure. So as you may already realize, there's no HA at the proxy level, as the proxy layer, and the truth is that what we decided is that if for some reason that proxy fails, the region was going to be marked as unavailable. So the traffic manager will not send any traffic to that region until that proxy was recreated or reprovisioned. So that's the way we solve, or we dealt with proxy layer failures. There is an option. There's an article out there about how to set up a ProxySQL with keep alive D, so you can get some HA at that layer. But we did not implement that for this project. So if the MySQL master fails, again, MHA will promote a new master from one of the other slaves, and ProxySQL will take care of redirecting writes and reads. So writes for the failed region, reads for the failed region to another slave, and writes for the two regions to the new master. And again, if a slave fails, again, ProxySQL will also take care of redirecting your reads to any of the available slaves. So of course there are some limitations. As I said, there's no HA at the proxy level. We talk about how to deal with that. So writes need to cross a one link, right? In 2 out of 3 regions, so that could also be a limitation. Again, it was good enough for this project, but in some cases, perhaps it may not be enough. So another thing is that ProxySQL will not only monitor that your server is live, but it will also monitor the status of the read-only parameter or the read-only setting. Any servers that are not read-only will be considered as masters. So that's something you need to keep in mind. If for some reason a server the read-only is disabled, then ProxySQL will start sending writes to it. So that's why it's important to have your read-only enabled or on your configuration file in case that server gets restarted. Again, fencing could definitely block a failover, as I said before. I mean, in normal conditions, updating your ProxySQL configuration should work and should be fast enough to allow failover to proceed. But if for some reason the MHA is not able to update the proxy configuration, or is not able to shut down the instance, or the instance shutdown is taking too long, well, you would have to wait for that to complete. And that's kind of the way the MHA manager works. It needs to be restarted after failover. So you need to restart MHA on a surviving region. Okay, and there's some time for Q&A.
Any questions? Yeah, come to the mic, please.
I'm not sure how old this case study is, but did you consider at this point using ProxySQL 1.4 with its HA abilities on its own, or was this using ProxySQL in like sort of Little Islands mode?
So are you referring to the ProxySQL cluster?
Yes.
Well, this is from last year. So thanks for the question. So ProxySQL is currently working on a feature to replicate configuration across the different proxies or different instances of the proxy. But that option is still a beta. It's not generally available. Today it's not generally available, and last year it was not an option. So that's why we did not consider that.
Thanks for the talk. Does ProxySQL have any capability of handling the read after write problem, or if an application writes in a non-primary site and then expects to read that data back before the data has replicated to its local slave? Is it able to handle that condition?
So as far as I understand, the way so you can create a set of rules, right? And as I said on one of the slides, you could add some sort of comment to your SQL text, like this like read read consistency or something, and you can create a rule based on that comment. So SQL proxy will redirect that read to the master instead of the slave.
Okay.
You can create any. So ProxySQL will analyze your SQL text. So you can include any comments there, and then create a rule with a regular expression to match that tag.
Okay, great. Thank you.
Okay, any more questions? Okay, let's thank the speaker.
Thanks everyone.
Thank you.